Hello, my name is Berna Koçkar. I'm an MSc student in Electronic Information Engineering in Trinity College Dublin. Today, I will be presenting an application of AI, specifically deep learning, on diagnosing medical conditions through medical images. We will be focusing on segmentation and classification of breast tumor images with deep learning methods. But how do we exactly diagnose these images? We are making use of convolutional neural networks, or CNNs for short. This is a particular deep learning method tailored for image classification tasks. These networks take images and through convolutional layers, they obtain local features, which they then use to classify these images. These features, which are also often called parameters, can reach to tens of millions or even billions in particular cases. To train these networks, we generally need thousands of images. However, in medical cases, we have a limited number of images. That's why we are employing transfer learning, which is a pre-trained network with some very useful features applicable to many image classification tasks, including medical image classification. The medical images we can use can be either X-rays, they may be MR images or ultrasound images or more. For breast tumor classification, we are using ultrasound images. Here on the left, we are seeing an example of ultrasound image. This particular example shows a benign tumor. Segmentation tasks include dividing this image into regions defined by edges in the image. These images can either be normal or they may contain a tumor which may be benign or malignant. We try to classify these images into three categories of normal, benign, or malignant as correctly as possible. Like we said, transfer learning is a powerful method for a task that does not provide many images. But additionally, we may increase the number of images by creating synthetic images, which is called the data augmentation. We create these images by zooming, flipping, or rotating, or color adjusting the originals. Like previously mentioned, deep neural networks can quickly reach an astonishing number of parameters, and this may be computationally expensive. To reduce this burden, we choose a compact and lightweight network model, MobileNet V2, with fine-tuned top layer for classification tasks. For segmentation task, we employ a UNet model modified for computational efficiency. The model training process can be summarized in three steps. First is data preparation and augmentation. On this step, we are creating synthetic images, then normalizing all of them, both synthetic and original images, shuffling and then separating them into train and validation sets with an proportion of 80-20. For segmentation step, we construct a UNet model characterized by skip connections for obtaining both low dimensional features and high dimensional features. This network consists of encoding and decoding blocks, which are made of several convolutional layers. We are simplifying these blocks to obtain a lighter network and finish with approximately 2.7 million parameters. For classification step, we are importing MobileNet V2, then freeze local feature weights and add the final top layer for fine-tuning network with our prepared images. On this network, we have approximately 4.6 million parameters, which is quite compact compared to other image classifiers like ResNet 50, which has about 25.6 million parameters. After training our model, even with reduced parameter count and lightweight network, we see that we have a very good accuracy that reaches up to 91% after epoch 10. This is a very good result for medical imaging tasks. In brief, our aim was to create segmentation maps and classify breast tumor images with deep neural networks. As we had a limited number of images, we used data augmentation techniques. Then we created a computationally efficient network using principles of UNet and transfer learning with MobileNet v2. In results, we saw an exceptional accuracy above 90%, which is comparable to larger and heavier networks. Thank you for listening.